In today's video, we'll discuss spring force and elastic potential energy. The spring force can be defined as the force used in stretching or compressing a spring. The potential energy from a spring is a conservative force, and the force of a spring can be calculated by using Hooke's law, which states that the spring force is equal to the negative spring constant times the displacement when the spring is stretched or compressed. An energy can be stored within a spring when work is done to compress or stretch a spring. The stored energy, or potential energy, can be calculated by taking 1/2 the spring constant times our displacement squared, which gives us a rising to a new work energy theorem, which involves our change in kinetic energy plus our change in potential energy due to gravity plus our change and potential energy due to the spring. And since our work of non-conservative forces is equal to 0, define the equation as our initial kinetic energy plus our initial potential energy due to gravity plus our initial potential energy due to the spring is equal to our final kinetic energy plus our final potential energy due to gravity plus our final potential energy of the spring. In our first example, we're asked if one end of a horizontal spring with a spring coefficient of 80 newtons per meter is held fixed while an external force is applied to the free end, stretching it slowly from 0 centimeters to 4 centimeters. Find the work done by the applied force on the spring. So, we're trying to find the work done, so we know the work done on a spring is the same as the potential energy of the spring, which is defined as 1/2 the spring constant times the displacement squared. Or if a force versus displacement graph is given, we can find the area underneath the linear line to solve for the work done. Either way, we can solve for the work done by the applied force. So our work is equal to 1/2 times our spring constant, which is 80 newtons per meter. And we see that we have a displacement of 4 centimeters. However, since our spring coefficient is in newtons per meter, we'll have to convert our displacement into meters. When we convert our centimeters into meters, or divide by 100, we'll get 0.04 meters squared. And when we calculate this through, we'll see that the work done by the applied force on the spring will be equal to 0.064 joules. In part B, we're asked to find the additional work done in stretching the spring from 4 centimeters to 7 centimeters. So yet again, we can use our force times displacement graph to solve for the area underneath the linear line, and then subtract the area from our big triangle from the area of our small triangle. So if we found the area of the large triangle, we see that the area is 1/2 times our spring constant of 80 newtons per meter times our displacement squared, which is now 7 centimeters. After converting to meters, we'd get 0.7 meters squared, which will give us a work done of 0.196 joules. And so we're asked to find the additional work done. So we can take the total amount of work, which is 0.196, minus the initial work that was done, which was 0.064 when the spring was stretched 4 centimeters, will give us a value of 0.132 joules of additional work were required to stretch the spring from 4 centimeters to 7 centimeters. In our second example, it states that a 50 kilogram circus acrobat drops from a height of 2 meters straight down onto a springboard with a force constant of 8 times 10 to the third newtons per meters. By what maximum distance does she compress a spring? So first, if we summarize the information given, we're given the mass of the acrobat is 50 kilograms. The maximum height of the acrobat is 2 meters, and the spring constant is 8.00 times 10 to the third newtons per meter. And we're asked to find the maximum distance the springboard compresses. We can use our new work energy theorem, which states the final kinetic energy plus the final potential energy due to gravity plus the final potential energy of the spring is equal to the initial kinetic energy plus the initial potential energy due to gravity plus the initial potential energy of the spring. So we see that once the board is fully compressed, the acrobat is stationary. Our final kinetic energy is equal to 0. Our potential energy due to gravity is also equal to 0. And since the spring is compressed, we'll have a final potential energy of a spring. Our kinetic energy initially will be equal to 0. We will have initial potential energy due to gravity. However, there won't be an initial spring constant since the spring isn't compressed. So if we rewrite the equation, we'll have our final potential energy of the spring is equal to 1/2 times our spring constant times our displacement squared is equal to our potential energy due to gravity, which is our mass times gravity times her height plus her displacement when the spring is compressed. Since we're trying to solve for d, we can get d squared by itself by timesing 2 by both sides and dividing by k by both sides will give us an equation of 2 times mg times h plus d divided by k. We can plug in the values into our equation. Since we know the mass is 50 kilograms, the acceleration due to gravity is 9.8. Our height was 2 meters plus d with a spring constant of 8.00 times 10 to the third newtons per meters. And when we calculate this out, we'll see that d squared is equal to 0.123 d plus 0.245. If we subtract 0.123 d and 0.245 to get the equation in its quadratic formula, we'll have d squared minus 0.123 d minus 0.245 is equal to 0. By using the quadratic formula, we can solve for d. So if we plug in our values, we'll have plus minus the square root of b squared minus 4 times a times c all over 2a is equal to d. When we take the positive square root of our quadratic formula, we'll get the final compression of the springboard to be 0.560 meters.